In this video, we will be continuing our work in Chapter 4, looking at Section 5 on absolute maximums and minimums. Okay, we've talked about local maximums and local minimums, and that just means there's a maximum or a minimum relative to a certain area. But when we talk about absolute maximums and absolute minimums, we're basically saying that there is one value that is the absolute highest value that a function gets to, or it's the absolute lowest value that a function gets to. We have our definition here. F of c is a local maximum if f of x is less than or equal to f of c for x near c, and a local minimum if it's f of x is greater than or equal to f of c for x near c. So it's relative to that local area around there. But like I said, we're going to look at these largest and smallest values within the domain to be our absolute maximums and minimums. Okay, so very similar definition, except here we're going to say it's for all x in the domain. So instead of for just an interval around the point, it's going to be for the entire domain, for it to be an absolute maximum or an absolute minimum. Okay, and again, these are called absolute extremum if it includes both absolute maximums and absolute minimums. Okay, I want to look at a few visual examples so you understand kind of what we're talking about. This particular graph, and we're really just focused on the graph, not so much the equation here. This particular graph, if you notice, has arrows going in both directions. Okay, so we do have a maximum here, but it's a local maximum because since there's an arrow here, this continues to go on and on and on forever. So there is no absolute maximum because it keeps on going forever. There is a local maximum. Same thing with the minimums. We got this arrow here, so it's going on forever in the negative direction. So this would be a local minimum, but it's not an absolute minimum because the function does continue lower than this value here. Okay, so on one like this, if we're looking for absolute extrema, what we see is we do have what would be considered a local maximum here at x equals 0. This would actually also be an absolute maximum because it never gets higher than this value here of 4. So a local maximum occurs at x equals 0, but also an absolute maximum occurs there because it never gets any higher than that. So the absolute maximum that this particular function ever gets to is 4. Okay, so that would be the maximum, the absolute maximum value would be 4. It does not have a local or absolute minimum because it's got these arrows down here and it's going on forever in the negative direction, so no local or absolute minimums. Okay, if we look at this one, we can see that here we do in fact have both a local and absolute minimum on this one because it does get to a lowest point, so the lowest value is 0. There is no absolute or local maximum because it goes on forever, keeps going up, 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 and so there is no highest value. Okay, we have an important theorem here, and it's called the extreme value theorem. And the extreme value theorem says if we have a function f that is continuous, so it's really important that we know it's continuous on a closed interval, so that's really important as well, then it has both an absolute maximum and an absolute minimum on that interval. So if it's continuous on a closed interval, you're guaranteed by this theorem to have an absolute maximum and an absolute minimum. And before we get into the algebra of this, we want to just look at it from a graphical standpoint. So this is just talking about the extreme value theorem. And so on this, we've got our polynomial, and it's on the closed interval from 2 to 12. Okay, so we can see that here, this first point is at 2, this one is at x equals 12, and it's all connected. So because it's a closed interval and it's continuous, we do have both an absolute minimum down here, and we have an absolute maximum up here. So we have a local maximum and local minimum here, but we are guaranteed to have these absolutes because it's on a closed interval. Okay, let's change the interval up a little bit here. So we're going this time from 4 to 10. Okay, so again, it's a closed interval and it's a continuous function. So we are guaranteed to have an absolute maximum and an absolute minimum. On the previous example, those endpoints happen to be our absolute maximums and absolute minimums. But on this particular interval, that's not the case. Our highest value is actually here and our lowest value is here. So our highest value is at 5, and so it reaches a value of 105. And the lowest, our absolute minimum, is at x equals 9, and it comes down as low as 73. So those happen not to be at the endpoint. So you can't just assume it's going to be at the endpoints that you have those absolute maximums and minimums. It could either be at the endpoints, or it could also be at these local maximums and minimums, which is where you have horizontal tangent lines, or another way to think of it, it's where your derivative is equal to 0. Okay, so changing this up again on a different interval, we've got the interval from 4 to 8. So in this one of the endpoints is an absolute, but the other one would not be. And so here we've got our absolute maximum is occurring at a place where our derivative is equal to 0, and then our absolute minimum is occurring at the endpoint. Okay, this one we're looking at the interval from 3 to 11. So what happens is on this one, we actually have 2 places that reach the highest value. So the highest value this takes on is going to be, turns out, 105, so it's a little bit higher here. So about 105, but it does that 2 times, okay? So both of these would be considered absolute maximums because they hit that highest value twice. So we would have absolute maximums at 5 and then again at 11. Okay, so we have a process for locating our absolute extrema. Absolute extrema, if they exist, must occur at critical numbers or at endpoints. So that's really the things we want to look at. The first thing, make sure you're talking about a continuous function on that interval. So it might not be continuous for all values, but as long as it's continuous on the closed interval, you're okay with that. You want to find your critical numbers in the interval itself. So your critical numbers, if you recall, is when your derivative is equal to 0 or when it's undefined. Okay, so once you've found those critical numbers, you want to evaluate the function f. Okay, so evaluate the f function at both the endpoints and the critical numbers. The absolute is going to be, absolute maximum will be the largest of the values that you find. The absolute minimum will be the smallest of the values that you find. Okay, so let's put this, those steps to practice here. We've got this function. It's a polynomial, so it's going to be continuous for all values of x. So certainly on this closed interval, it's going to be continuous. So we need to, in doing our absolute maximums and minimums, when you're finding absolutes, we're going to make a table. Okay, on that table, we're going to have our x's and we're going to have our f of x. Okay. These are the numbers, these are going to be the numbers where we could potentially have an absolute maximum or an absolute minimum. So we know on a closed interval, our absolute maximums and minimums might occur at the endpoints. So I'm going to list those as possible candidates. And the other place are our critical numbers. So to find our critical numbers, I need to find where the derivative is either 0 or undefined. In this case, there's no undefined places. So we just have to focus on where our derivative is equal to 0. Okay, so the easiest thing is going to be to factor this. So I'm going to take out a 3 as a GCF. Actually, I'm going to take out a 3x as the GCF. Okay, so I'm going to take out a 3x as the GCF, and that's going to leave me with an x minus 4. Okay, so that means that if I set this equal to 0, I could get one of my critical numbers. And then if I set that equal to 0, I'm going to get the other critical number. So I'll have just 0 here, and then here I'm going to have 4. Okay. Okay, so once we've got our endpoints and we've got our critical numbers for the first derivative, Now we want to plug each one of these numbers into the original function. So not the derivative, but the original function. So I need to figure out what f of -7 is. So I'm going to do -7 to the third, following this function, minus 6 times -7 to the second. And that's going to give me -637. All right, then I'll do f of 7. And that's going to be 49. If I put 0 in, that one's easy. 0 is just going to be 0. And then if I put f of 4 in, you can verify this, but f of 4 will be -32. Okay, so by the extreme value theorem, we found that we're guaranteed that if our function is closed and it's on a closed interval and it's continuous, then our absolute maximums and minimums exist, and they're going to be at either the endpoints or the critical number. So it has to be some of these values here. So we want to look and just see like which value of these is the largest. Okay, so 49 is the largest. So that's going to be my absolute maximum. It's going to occur at x equals 7, and the maximum value, anytime it says value, that's the y coordinate. The maximum value is 49. So the highest that function ever gets on this interval is 49. Okay, and then our absolute minimum, we're going to look at these numbers and pick the smallest one. So here's my smallest. So my absolute minimum occurs at -7, and the minimum value, the absolute minimum value, is -637. Okay, here's one very similar for you to practice with. All right, we'll start. Okay, so we're going to start by making our little table, because again, we have a continuous function on a closed interval, so we can go ahead and make the table. So anytime you're doing absolutes, make a table like this, do a sign chart for your locals. Okay, so we've got -3 and 5 for our endpoints, and then we need to find our critical numbers. So our critical numbers will come from our derivative. So 3x squared minus 12. We're going to take out, in this case, we're going to take out a 3 as the GCF. And this is the difference of squares, so I'm going to factor it x minus 2 and x plus 2. So I get, when I set this equal to 0, I get 2. And when I set this one equal to 0, I get -2. So I have 2 and -2 as critical numbers. Okay, so we want to plug into the original function. So that would be -3 to the third minus 12 times -3. Be really careful with your signs on problems like this. That should give us 9 for that value there. If I plug 5 in, f of 5, and you can double check me on this, f of 5 is going to be 65. F of 2, plugging 2 in, is going to be -16. And then f of -2 is going to be +16. Okay, so we can look at this and see this is our largest, so our absolute maximum is going to be at 565. And then our smallest value is here, so our absolute minimum is going to be at 2, -16. Okay, we want to look at the second derivative and how that relates to extrema. So if we have a situation where we have the first derivative is equal to 0, okay, so basically we're looking at something where we have a horizontal tangent line, and we know that the second derivative is greater than 0, which means it's concave up, then the two statements together tell us that I'm working with a local minimum here because of the fact that I had that horizontal tangent line and the concave up situation there. If we turn this around and I have, again, the first derivative equal to 0, but this time the second derivative is negative, then it's concave down, and that means this would have to be a maximum that's occurring there. Okay, so the second derivative test says if we have some critical number c of the function f of x such that f prime of x is equal to 0. So in other words, it's a critical number of that first derivative. And then the second derivative is greater than 0, we're working with a local minimum. And if the second derivative is less than 0, we're working with a local maximum. So this kind of summarizes it. Your first derivative, if it's 0 and the second derivative is positive, then we have the local minimum. If the first derivative is 0 and second derivative is negative, it's concave down, so we have a local maximum. But if the first derivative is 0 and the second derivative is 0, we actually can't apply the second derivative test. Okay, so what this basically does is it lets you substitute this process in the place of doing the sign chart that tests for local maximums and minimums. So let's kind of see how this applies. It says find the local maxima and local minima for each function. Use the second derivative test when it applies. Okay, so I'm going to have the first derivative of this function, which is 3x squared minus 18x plus 24. And I'm also going to end up needing the second derivative test, the second derivative. Okay, so that's going to be 6x minus 18. Okay, so we want to find where this first derivative is equal to 0, right? So we want to set 3x squared minus 18x plus 24 equal to 0. So I'm going to take out my GCF, which is going to be 3, and that leaves me with this. And then this is just a trinomial that I'm going to factor. So I need to think what multiplies to give me 8 and adds to give me 6. So that's going to be -2 and -4. Okay, so when I set each factor equal to 0, I'm going to get 2 and 4 as my critical numbers. Okay, so that part is kind of the same. Prior to this second derivative test, what we would do is we would do our number line, we'd put the 2 and the 4, and we'd look at our first derivative and our second derivative, and we'd figure out where it's increasing and decreasing, and that would tell us where we have local maximums and local minimums. Instead of doing this, we're going to replace this with the second derivative test. Okay, so the second derivative test tells us that if we take these critical numbers and plug them in to the second derivative, then it's going to let us know whether it's a maximum or a minimum. Okay, so if I take the second derivative and I evaluate it at 2, which is the first of my critical numbers, that gives me a negative. Okay, so a negative means it's concave down. So if something's concave down, then it means that must have been a local maximum. Okay, if we look at our second derivative test applied at our critical number of 4, that's going to give us +6. So that means it's concave up. So we have a local minimum. Okay, so this kind of takes the place of the sign chart. Personally, I'm going to leave it up to you as to which one you do. I'm not going to, as long as you show me one of those, you've proven that it's a local minimum or maximum. You don't have to do both. Okay, so on this one, same process. We're going to look at our first derivative here. So the derivative of e to the x is e to the x. The derivative of 5x is 5. Our second derivative would just be e to the x because the derivative of 5 is 0. So if I'm looking for the critical numbers, I'm going to set that derivative equal to 0. So I'm looking for where e to the x would be equal to 5. And we've done enough with these to remember, hopefully, that to get rid of the e, you use the natural log. Okay, so the only critical number I really have is the natural log of 5. Okay, so if I then take and I plug that back into this, so I'm going to plug in the natural log of 5. So e in the place of x, I'm going to put natural log of 5. And hopefully you remember your exponential rules here, that when these are together, that's going to just equal 5. What's really important is that it's positive. Okay, so if it's positive, it's concave up. So we have a local minimum. And that local minimum, the x coordinate would be the natural log of 5. And if you wanted your y coordinate, you would just plug it back into the original function. And these get a little messy, but they're not terrible. Okay, so here those would cancel and we would have 5 minus 5 natural log of 5. Okay, so the last example here, we want to use this one. So we'll take our first derivative. That's going to be 60x to the 5th minus 120x to the 4th plus 60x to the 3rd. And our second derivative, this is going to be 300x to the 4th minus 480x to the 3rd plus 180x squared. All right, if we want to get our critical numbers here, we're going to take out 60x to the 3rd. Okay, because 60 is a GCF, and then x to the 3rd would also be a GCF. So we'll have x squared minus 2x plus 1. And the good news is, even though it started out pretty nasty, this actually factors pretty easily to just being x minus 1 and x minus 1. So our critical numbers, we've got 3 different factors. So we get, if I set 60x to the 3rd equal to 0, I'm just going to get 0 as a critical number. And then here I'm going to get 1 as a critical number. Okay, so I'm going to go and I'm going to plug in each of these. Okay, so when I plug 0 in, I'm going to have 0 minus 0 plus 0 is 0. So this one is actually inconclusive. If I plug 1 in, I'm going to have 300 minus 480 plus 180. And that one is also going to be equal to 0 and be inconclusive. So in these cases, the second derivative test didn't help us. It was kind of a waste of time for us. So we would still need to put these numbers on our sign chart in this case. Okay, so we want to look at what's happening here. So something between, let's pick something greater than 1. So that would be a positive, and a positive. If I pick, say, 1/2 here, that's going to be positive, negative, negative. And then here, if I pick -1, that's going to be negative, negative, negative. So I'm going to have a negative here. So I'm going to have a decreasing function and then increasing and increasing again. So if I decrease, then increase, that means that I have a local minimum at 0. And then here, I didn't have a sign change, so I don't have a local extreme at x equals 1. And as far as coming up with this value here, I'm just going to plug in the 0 to that function, and I'm going to get 0 out, and that gives me this value.